Okay, so today we're going to try to skim over the magnetism unit, and first we're going to start off with types of magnets. So we have permanent magnets right here, and they are all the dipoles in the atoms are aligned, so it makes it a magnet. And there's iron magnets, any kind of magnet that has random dipoles but easily movable to align. So say you get a screwdriver and you scrape it against a permanent magnet. That permanent magnet will align the dipoles inside the iron to make the iron act like a magnet for a little bit. So if you've ever scratched a screwdriver against a permanent magnet and try to pick up a staple, it'll pick it up because it acts as a magnet. And then we have electromagnets, just a loop of current carrying wire coiled around a piece of iron in a magnetic field. And we can go ahead and try to pull up an image of an example of an electromagnet, if I can get that real quick, right here. Here is the cord, the piece of current carrying wire right there, and this will be the positive side, and this is the negative. It's flowing from positive to negative, aligning the dipoles inside your piece of iron right here from positive to negative, making the electric field out here also flow from positive to negative over here. Okay, so now we're going to move on to the right-hand rule. As the right-hand rule is a pretty simple little rule to keep up with or understand. So basically you have your three fingers right here, your thumb, your middle finger, and your pointer finger, and they're all going to be, to use the right-hand rule correctly, you need to have all three fingers perpendicular to each other. So, say in the diagram, your thumb would be pointing up, and your pointer finger would be pointing outward, both in the position like a little gun, and then your middle finger will be pointing kind of an awkward position outward, and they'll all be parallel to each other. So that's how that works. And each finger is assigned to the magnetic field, velocity, or force, and they all point in each direction, respectively. So your pointer finger will be the velocity, and the easy way I remember velocity is your pointer finger is because whenever you want to point at something and say you go that way, you point with your pointer finger. So velocity is your pointer finger. Force is your thumb. Easy way to remember that is I don't know, I think of the thumb as being a powerful finger because it's opposable thumbs. So I assign that as force in my head. I don't know why. And then magnetic field is your middle finger. And then here we can go ahead and try out the right hand rule. So right now I'm going to draw a diagram with a charge, a positive charge right there, moving to the right. We want to go ahead and label out our three fingers right there as B, V, and F. B being our magnetic field, V our velocity, and F our force. So if the particle is moving to the right, you want to write down velocity to the right, and our V is into the page as represented by the dots in the picture going into the background. So that must mean our force is actually not up, it is down, if we use the right hand rule right. So the force on a wire, it's essentially the same idea. You're going to have a the current instead of a wire. It's moving from right to left, or left to right, positive to negative. And right hand rule with a wire, all you want to do is use your thumb to point in the direction of the current. And if you go ahead and do that real quick, you notice that the current is kind of coming over the wire, kind of like this. It's kind of hard to, it would go behind the wire and come back over, kind of like, I can't really describe it too well, but hopefully you understand. It'll be coming over the wire kind of like that. Ignore that first one, it's a mess. That's how force on a wire works. So okay, now we're going to move on to velocity selectors. And velocity selectors are pretty cool. They involve about 3 chambers. Right here is the first chamber. It's a 2 plates right here on this side. If we can get it to right here on this side. It's 1 plate, or 2 charge plates. Sorry, these 2 charge plates right here on each side, connected by a battery up here. So this side is the negative side, and this side is the positive side, if you can tell. And we have a charge that is going to be shot through an opening, through 2 little separate chambers. The first one right here is a magnetic field and a electric field, both bouncing out to keep the charge to go through just fine. And then over here we just have the magnetic field causing the charge to kind of arc like that. Hopefully we draw that again. There you go. And our charge is positive over here. And if we use the right hand rule, we notice that our force for the magnetic field will be downward. If we use the right hand rule, that's why whenever over here in the second sector, the sector 2 over here, that's why the charge goes down and makes this kind of arc over here. So our force is down, and that must mean that we need an opposing force that's equal to the magnetic field force. So we do the right hand rule on our electric force, and if we just use common sense, we've got the negative side of it up here, as we stated before. We've got that up here, and then the positive side is over here on the bottom. And positive and positive repel, and positive is attracted to the negative. So the electric field force is up, but the electric field is down, but the force is up whenever it's positive. Okay, and we want to go ahead and learn how to do forces on particles, and that's just this equation out right here. Force equals velocity. This is our velocity. Velocity cross B. All 3 of these things are going to be parallel to each other, just like the right hand rule. That's what the right hand rule is describing, essentially, is this equation. And our force over here on this side is just the magnitude of the force, and the magnitude of the force is equal to the velocity times the field, the strength of the field, sine theta, the angle in which it is crossed with in which it's parallel with the other factors. And what we are looking for, what is ideal, is to have sine theta equal 90. 90 is whenever we get everything to be perfectly parallel with each other. Um, okay, and our magnetic field, in this equation, it equals to mu. This is mu times the current over 2 pi r, and r is from the velocity selector. This is our r right here. That's an r. That r goes into this equation right here. Is that? And just to wrap things up, we're going to go ahead and start trying to introduce you to the electromagnetic induction, which I thought or found to be pretty easy. So, what all of this is up on the screen, electromagnetic induction is a changing magnetic field producing a voltage or EMF, and this is our symbol for EMF. It's kind of like a backwards 3 with a little line on top of it. And that's Faraday's law, or also known as Lenz's law. And flux. Flux is this part up here. This is the magnetic field strength times the area of the loop of wire that's being put into the magnetic field. That creates flux, and we just put that over time, change in time, to get our EMF over here. It's a pretty simple process. If we go ahead and go through this. So Faraday's law, it's a little bit of a simple thing. Just if you follow these steps. Oops, went too far. B equals is essentially our T. That you can, while you're doing Faraday's law, you can think of B as T, and T is Tesla's. So, in a minute, I'm going to give us an example of how to use Faraday's law, and I'm going to give you a problem. And this will make sense, but for right now, your steps you want to go in is you want to figure out the direction of the magnetic field, whether that be into the page, out of the page, to the right. You wanted to figure out the direction of the magnetic field first. Then you want to figure out if the magnetic field in the loop of wire is increasing or decreasing. Because if it's increasing, then the change in B times A over T is, if it's increasing, then that is with the direction of the magnetic field, but if it's decreasing, it is against it. That's what 3 just said, sorry. And then 4, the induced field is opposite 3. So whatever you get for 3, your fourth step, the induced field, be induced, will always be opposite of the third one. So we're going to go ahead and draw an example right here. So this is our loop of wire right here, and it's moving to the right inside of a, this right here is our magnetic field with the dots again into the page. It's moving to the right, so we can go ahead and label out all our things over here. Go ahead and draw out the problem right there. Okay, so it's asking me to find the amplitude and the direction of the induced current from the image below. So let me lower this real quick. So we're going to be trying to find the direction and the amplitude with these things over here, and we have our time, our area, our Teslas, and our resistance, our resistance over there. And the equations we're going to be using is I over voltage, or I equals voltage over resistance, or EMF over resistance. And we're also going to be using, to get EMF, we're going to be using, if we can go back because we went too far. For EMF, we're going to be using this equation down here, change in the magnetic field times area over a change in T. Okay, so now that I know all the equations and I have everything labeled out over here, I'm going to go ahead and try to solve this problem. So I'm going to redraw it out. And we're going to try to find the direction of the induced current first, so that we can find the amplitude later. So if we look at it, our B is into the page. So if our B is into the page, and over here, we change colors real quick, and over here our loop of wire is increasing into the magnetic field, then B times A over T will be with B. So they're both into the page, and then B induced will then be out of the page, making B induced is out of the page. Then our right hand rule, if we stick our thumb up into the air and we see that our fingers curl into this kind of shape right here, we can tell that our current is going this way around the loop of wire. If we can draw arrows. So after we found out the direction of the induced current, I'm going to go ahead and try to find out the magnitude of it. So we're going to be using these little things over here to help us out, help us try to find that. So we're going to set up our first equation with EMF equals change in the magnetic field times area over change in T. So we just want to plug everything up, and we're going to go ahead and do that right here. So our change in B is right here, T, so it's 10, I'm going to put 10 there, and area is right there, and resistance, 2, that's it. And that that equals 2.45 volts, or EMF. So once we have 2.5, we want to go ahead and use this equation now. Our current is equal to the EMF that we just found, which is 2.5. I already have that written down. And then our resistance is still, I believe it was 2 from the last slide. Yep, 2. And you go ahead and plug it all in. And it's pretty straightforward, and it gives you a 1.225 for our current in amps. Forgot to write that in. And that is how you do Faraday's law with electromagnetic induction.